guys, and welcome to lesson 4.8, solving trig equations involving compound angles. So we'll first start off with this example here, cos of 2x plus cos of x. Now you'll notice that in both of these terms we both have cos, but the arguments of the angles are different. So your goal here is you want to write everything in terms of cos x. So what we can do is recall the identities for a double angle for cos that we learned in the last lesson. Now I know that there are three options, two of which have both cos and sine in it. Now ideally it would be nice if all of your terms were just terms of cos. So the identity that I'm going to choose for this cos 2x is going to be 2 cos squared x minus 1. Okay, so that way our terms here are just coses and 1s. We're not dealing with coses and sine. And now, because our arguments are both just x, we can write this kind of like a trinomial. So 2 cos squared x plus cos x and then minus 1. So it's like a trinomial where our exponents are in descending order. So we can treat it like a trinomial that you can factor. So you want to find two numbers that multiply to -2 and add to +1. Okay, so those two numbers are going to be +2 and -1. So we can do the decomposition here. 2 cos x and then plus 2x or 2 cos x minus cos x and then minus 1. And now we can do some grouping. So I look inside this first group and I see that 2 and cos x are common. So that would leave me with a cos x plus 1. And I look at my second group here and we can common factor out a -1, leaving me with cos x and then plus 1. And because these two brackets are identical, I can common factor those out. So we're left with cos x plus 1 and 2 cos x minus 1. And so we'll treat this like any other solving question that we've done in the past. We let each bracket equal 0 and isolate. So our first equation here is, where does cos x equal 1? Whenever your trig function equals 1, 0, or -1, I always like to think of their graph. And I know that cos is equal to -1 when my angle is at pi. So one possible value for x would be pi. Okay, let's move on to our second bracket here. Set it equal to 0 and then isolate cos x. So I'll move the 1 over and divide by 2. So when does cos x equal +1/2? So I'll draw out my quadrants here. I know that cos is positive in the first and the last quadrant. Again, I can recall that cos is x over r, so my x values should be 1, my r values should be 2, and this does look like the makings of a special triangle, so that would hint to me that the angle, the related acute angle, would be pi/3. So we're going to have two values for x, start at standard position and rotate counterclockwise. So our next value for x would just be pi/3. And then our final value for x, start in standard position and rotate counterclockwise. So we almost went full circle. We almost went 2 pi. But we stopped pi/3 before that. So our final answer here would be 5 pi/3. So to conclude, we've got three values here, or three possible answers here for x. Okay, so that would be it for this question here, and we'll move on to example B. So looking at this, I see that on the left side here, that does look like the expansion for the difference identity for cosine. So I'll write that out. And we can simplify that further and say that this is cos 2x equaling -1. Now, what we have here is a double angle. Our goal here is to solve for x. So there are two solutions that I'm going to show you, or two methods here. So solution 1, we can use the double angle identity. Again, you don't want to use the double angle identity where you have both cos and sine in it. I'm going to choose the 2 cos squared x minus 1 identity, and that is equal to -1. Okay, so I'm going to do what we did on the last page. I'm going to isolate for cos x. So first I'll move the 1 to the other side. So 2 cos squared equals -1 plus 1. I'm going to divide both sides by 2, and then we're going to square root both sides. And now normally I'd write plus or minus the square root of something, but the square root of 0 is just 0. The solution will come for when cos x equals 0. So I'm going to take a quick look at our cosine graph, and I notice that the graph of cosine hits 0 at pi by 2 and also at 3 pi by 2. Okay, and I'm going to show you a second solution, which is actually going to be quite helpful for some of the future examples that we're going to do in this lesson. So the other way that we can get to this answer of pi by 2 and 3 pi by 2 is to change the interval that we are used to. So we're going to scroll up just for a second. Actually, I'll back page. The question said, solve each of the following equations for this particular range. So when I go ahead and say change the interval, we're talking about this. Because in this domain here for x, we are working with just x is being between 0 and 2 pi. But our question says cos of 2x. So what we can do is we can multiply each one of these by 2 so that we have an interval that fits the angle that we're working with, or the argument that we're working with. Okay, so we're no longer focused on between 0 and 2 pi, we're going to be focused between 0 and 4 pi, because our angle is not x, it's 2x. So basically what we want to do here is find out when cos of our argument equals -1. So again, I'm going to take a quick look at our cosine graph. Think of your angle. So cos of what angle is going to give us -1? So when you take a look at your cosine graph, I know that my argument, or my angle, must be equal to pi, so that my cos graph would give me a value of -1. So my angle here must be equal to pi, so that cos of that would be -1. Now this is great if you're thinking in terms of between 0 and 2 pi. But remember, we need to extend this interval up until 4 pi. So basically what you want to do is you want to take your argument and what it equals, so 2x equals pi, and you want to add another 2 pi to it, okay? And in both cases, you don't want to solve for 2x, you want to solve for x. So what I'm going to do with this first equation here, if I divide both sides by 2, we're left with x is equal to pi over 2. For the second equation that we came up with, I know that my argument is equal to 3 pi, and if we're going to solve for x, we divide both sides by 2. So our second possible answer is 3 pi by 2. So using this method does end up giving us the same result as above, but this method is actually going to become more useful, as you'll see in the next example. But before we go ahead and move on to that, let's just kind of take a look as to why this works out. Cos of some angle equaling -1. Now if you take a look at the graphs here, the red graph represents cos of x. So between 0 and 2 pi, cos of x only hits -1 at one point. But when you have the graph of y equals cos of 2x, well, let's think about that for a second. The period for the graph of y equals cos 2x is going to be 2 pi over the k value, which in this case is 2. So the period is really horizontally compressed. The period has went from 2 pi to now pi. Well, between 0 and pi, we see that the cos graph hits -1 at one spot at pi by 2, which is what we found on the other page. But remember, we need to solve between 0 and 2 pi. So essentially, cos 2x has 2 cycles in between 0 and 2 pi. So that's why we have that second angle, or that second value, where cos hits -1. Okay, so let's go ahead and move on to the next example and try to solve for x here. So on the left side here, I see that this is the expansion for this difference identity for sine. So I know that we have, if we're going to simplify this, it's going to be sine 5x minus x equals √3/2. And if we go ahead and simplify that a little bit more, we have sine 4x is equal to √3/2. Now in the last example, I showed you 2 different ways. The first way was use the double angle identity. Okay, well if we go ahead and do that, well the sine double angle identity was 2 times sine of half the angle, so 2x, times cos of half the angle, 2x, equaling √3/2. Now if you take a look at what we've got here, well we have sine 2x and cos 2x. So what we have is a term here that has both sine and cos in it. We can go ahead and simplify this further, but it's just going to end up having lots of sines and lots of coses. So using the double angle identity in this case is not helpful. Okay, so this is why doing solution 2 will work out. We're going to change the interval. So essentially what we do is we normally work between 0 and 2 pi, but since our question is sine 4x equals √3/2, what we want to do is kind of multiply each one of these by 4 because we want to work with 4x. So we're working between 0 and 8 pi. Okay, well, how does this work out? Well, first think in terms of between 0 and 2 pi, just like you normally would tackle this question. So sine of some angle is going to give me √3/2. Well, if I were to tackle this question, I would say, okay, well, √3/2 is positive, so sine is positive in the first quadrant and the second quadrant. I also know that sine is y/r, so my y value is √3 and my radius is 2. So that tells me that we have special triangles here. So my related acute angle would be pi by 3. So I would have 2 values for my argument. Start at standard position and rotate counterclockwise. So my argument is equal to pi by 3. And we can get a second value here. So again, start standard position and rotate counterclockwise. So we almost went pi radians, but we stopped pi by 3 before that. So the value of this blue angle here would be 2 pi by 3. Okay, so my argument is equal to 2 pi by 3. And just as we did last time, we want to solve for x. So what I'm going to do is divide both sides by 4. So our first possible angle for x is going to be pi by 3 divided by 4, which would give us pi by 12. The next would be x equaling 2 pi by 3 divided by 4, which would give me 2 pi by 12, and if we were to reduce that, we would end up with pi by 6. So just as we did in the last example, I want to kind of add that extra 2 pi. So I'm going to take these values here, and I'm going to add 2 pi to each of them. Okay, so I'm going to take that 4 pi or 4x equaling pi by 3, and I'm going to add 2 pi to it. And I'm going to do the same thing to our other equation. So now what we're working with is pi by 3 plus 2 pi actually ends up being 7 pi by 3. And the other equation is 4x equaling 8 pi by 3. Okay? And again, what we want to do is we want to solve for x. So I'm going to divide both sides by 4. 7 pi by 3 divided by 4 is going to give me 7 pi by 12. So that's our third possible answer here. And again, I'm going to do it to this equation. 8 pi by 3 divided by 4 ends up being 8 pi by 12. And I can actually reduce that to 2 pi by 3. So there's our fourth answer. So again, if it helps, you can kind of think of this as working from, and I'll put it in quotation marks, so between 0 and 2 pi. Think of this as being between 2 pi and 4 pi. But remember, our goal is to get to 8 pi. So what I'm going to do is, again, take this original statement, and well, I've already added 2 pi. What I'm going to do now is add 4 pi. So to work in the range from, let's say, 4 pi to 6 pi, I'm going to take that original statement that we said, so 4x equaling pi by 3, and I'm going to add 4 pi to that. And the other statement, which was 2 pi by 3, I'm going to add 4 pi to that. So now what we're working with is our argument 4x is equal to 13 pi by 3. And again, on the other side, or the other equation, we have our argument 4x equaling 14 pi by 3. And now, again, we want to get x all by itself. So I'm going to divide both sides by 4. So what we end up with is 13 pi by 3 divided by 4 will give us 13 pi by 12. So that's our fifth possible answer here for x. Our sixth possible answer, again, comes from dividing both sides by 4. So take your 14 pi by 3, divide by 4, and you should end up with 14 pi by 12, which can be reduced into 7 pi by 6. So at this point, we're just repeating the same procedure over and over again. So we kind of want to work from the last interval, which is between 6 pi and 8 pi. So again, I'm going to take that original statement where the 4x equals pi by 3 and the 4x equals 2 pi by 3, and this time, well, we've added 2 pi, we've added 4 pi, so now we're going to add 6 pi. So really what we're working with is our argument being 4x equaling 19 pi by 3. And again, 4x equaling 20 pi by 3. And then, again, we want to just solve for x, so I'm going to divide both sides by 4, giving us 19 pi by 12, which is our seventh possible answer for x. And then our 8th possible answer for x is take your 20 pi by 3 and divide by 4, which gives us 20 pi by 12, which can be reduced into 5 pi by 3. Okay, so what we do have here are 8 possible answers for x. We have, so a little long, but all of these answers are valid. Okay, so again, I'm going to show you visually why this happens. So we'll take a look at our sine graph. So our sine graph here is in red, and we're focused between 0 and 2 pi. Okay, and now our graph of y equals sine of 4x, well, the period for that would be 2 pi divided by our k value, so 2 pi over 4, which ends up being pi by 2. So every pi by 2, we start a new cycle. And within that cycle, our sine graph will hit root 3 over 2 twice, here and here. And in our next cycle, again, it hits twice. And you'll notice that from 0 to 2 pi, we actually repeat the cycle 4 times, which is why we end up with so many answers. Let's move on to another example. So this time we're dealing with a reciprocal function. So cosecant squared of 3x minus 1 is equal to 0. Again, so what we'll do here is we'll isolate cosecant so that it equals 1. And we also know that cosecant is really r over y. So if cosecant is equal to r over y, then its reciprocal sine, so sine squared, would be equal to y over r. And since y is 1 and r is 1, sine squared of 3x is equal to 1. Now what you want to do now is square root both sides, because you don't want to work with sine squared, you just want sine. So sine of 3x is equal to plus or minus the square root. So sine of 3x is equal to plus or minus 1. Okay, so again, we are going to change our interval. So normally we would work between 0 and 2 pi, but because the argument, the angle that we're working with is 3x, we're going to multiply each one of these things by 3. So really we are looking between 0 and 6 pi. Okay, so let's treat this as if we were working between 0 and 2 pi. Well, I would say, so sine of some angle is equal to positive or negative 1. So I would take a look at our sine graph, and we notice that when the angle for sine is equal to pi by 2, we get positive 1. So that means when our angle is equal to pi by 2, we get a value of positive 1. We also need to know when it equals negative 1. So we'll take a look at our graph again. When our angle for sine is equal to 3 pi by 2, we get negative 1. So when our angle is equal to 3 pi by 2, we get negative 1. So just like we did in the last example, we'll divide so that we get x isolated. So if I divide both sides by 3, pi by 2 divided by 3 would be pi by 6. That's our first possible answer. And then 3 pi by 2 divided by 3 would be 3 pi by 6, which ends up being pi by 2. So that's our second possible answer. And now again, remember we're working all the way up to 6 pi. So what we're going to do is think of working between 2 pi and 4 pi, which means I'm going to take this original statement that we created and I'm going to add 2 pi to it. So really we're working with 3x equaling 5 pi by 2 and 3x equaling 7 pi by 2. And as we've done for every other question, isolate x, so we'll divide by 3, giving us 5 pi by 6. That's our third possible value. And if we divide by 3, we end up with 7 pi by 6, which is our fourth possible value. Okay, so we're almost there. So now what we're going to do is work between 4 pi and 6 pi. So again, if I take that original statement, which was 3x equaling pi by 2, but this time add 4 pi, and same thing with the other one, then really what we're working with is 3x equaling 9 pi by 2 and 3x equaling 11 pi by 2. And again, we divide both sides by 3. So 9 pi by 2 divided by 3 is 9 pi by 6, which can be reduced to 3 pi by 2. So this is our fifth possible answer. And then finally, our sixth possible answer, take the 11 pi by 2 and divide by 3, and we end up with 11 pi by 6. Okay, and we know we don't have to add any more rotations or any more pi by 2 or any more 2 pi's because we've hit the maximum. So we're already at 6 pi, which is where we want to stop. So kind of as a final statement, that is it for this example. Okay, so finally, I'll leave you with this additional example to try on your own. It's very similar to the very first example we did at this lesson. So I'm going to stop here. This will be something that we'll take up in class tomorrow. But try and make sure that you're only working with cos of x. So the hint I'll give you is change your cos to x using the double angle identities that you learned from last lesson. So that is it for today's lesson, and if you have any questions, please ask in class. Take care, guys.